Hey everybody, this is Miss Berry. In this video, we're going to go over section 6.2, which is called Exponential Models. I'm going to go ahead and share my screen with you guys. We're going to do a ton of examples in this section, and hopefully you will see one of every type that you will encounter on the homework. Exponential models arise naturally in lots of different types of real-world scenarios. So the first type of exponential model that we will, or application of an exponential model that we'll look at, deals with population growth or population decay. So we'll talk about first models of population growth or decay. Of course, population growth would be when a population is increasing. Population decay would be when a population is decreasing. So it says the population of a certain inner city area is estimated to be declining according to the model P of t equals 446,000 times e to the negative 0.014 t, where t is the number of years from the present. What does this model predict the population will be in 6 years? Round to the nearest person. All right, so that e there is not a variable. That is the irrational number e. It is on your calculator. So let's go ahead, before we do anything else, let's take a look at our calculator and just take a minute and look at your particular calculator and figure out where your E button is. If you have the TI-83 or TI-84, then your E button will be in the same spot as mine. There's actually two E buttons on this calculator. Let's see if I can back this up a little bit and refocus. All right, so there's actually two E buttons. You can see one is right. Sorry, let me see if I can get this. Yeah, there it is right there. So you would hit second ln. That would take you to e to the x, which is what we'll be using. And if you don't have an exponent on e, you can use this button over here. So you would hit second, then the division button, and that would pull up just the little number e with no exponent. All right, so most of the time you'll be using that one that's over there on second ln for this class anyway. All right, so let's look at our problem. It says t is the number of years from the present. So they want to know, what is the population going to be in 6 years? So all we need to do is plug in t equals 6. All right, so p of 6. The population after 6 years is going to be 446,000 times e to the negative 0.014 times 6. All right, so let's plug that in our calculator. Just be really careful. Make sure you plug this all in correctly. All right, so 446,000 times e. Remember that second ln. So we're going to hit second and then ln. That's going to pull up e, negative 0.014 times 6. Okay, now if you are using the TI-83, then your calculator should have opened up a parentheses for you whenever you hit that E button. Now you would go ahead and close that, if you're working on the TI-83. All right, then go ahead and hit enter, and there is our population. It says round to the nearest person, which means the nearest whole number. This 3 here tells us that we're not going to round up. So it's going to be 410,066. 410,066. Now this number makes sense because they told us that the population was declining. So it should be less than our initial population, which was 446,000. I can tell that the original population was 446,000 because that's the number that's in front of, or the coefficient in front of E. So that's always the initial value of the population. Right, so again, this is sort of like the general model for population growth and decay. Looks like this. It is P of T equals A. They call it A0. Sorry, let me type that again. Sorry, write that again. They call it not A sub 0, P sub 0. Let me write that whole thing again. P of T equals P sub 0 times A to the T. P sub 0 is called your initial value. So again, that is how I was able to identify that 446,000 was my initial value for my population. And then A here is called the growth rate. The growth rate. Okay. Okay. All right. So let's look at another example. All right, so it says, a certain species of deer is introduced into a forest, and wildlife experts estimate the population will grow to P of T equals 299 times 3 raised to the T over 2, where T represents the number of years from the time of introduction. All right, so again, if we look at this, we can see this number out front, 299, that is the initial value of the deer. So they introduced 299 deers, not deers, excuse me, 299 deer at the beginning of this project. So that is our initial population. And 3 is our growth rate. All right, so it says, part A says, what is the tripling time for this population of deer? All right, so first we need to know, what was the initial value of deer, or the initial population of deer? We said that was 299. All right, so what would, how many deer would we have if it tripled? All right, so if the population tripled, then we would have 299 times 3. All right, so let's see, 299 times 3. So there would be 897 deer. Okay, so let's plug that into our function up here for P of T, because that's the population currently. All right, so we're going to replace P of T with 897. Right-hand side stays the same, so it's 299 in parentheses, then 3 raised to the T over 2. All right, so I'm going to make this larger again so I can write a little bit neater, hopefully. Trying to adjust that T a little bit. There, that looks better. Okay, so we're trying to solve for T because T is time. It says, what is the tripling time? All right, so we're going to divide both sides by 299, trying to get T by itself here. All right, so 897 over 299. 897 over 299 is, of course, 3, because that's what we just saw. We just saw that 299 times 3 was 897. So it makes sense that 897 divided by 299 would be 3. All right, so 897 divided by 299 is 3. And we can go over here and cancel this out. So we're left with 3 to the T over 2. Now again, we're trying to solve for T here. We're going to use some of those rules we learned in section 6.1 about solving exponential equations. We know that this is really like 3 to the first power. You can see that these guys have the same base. So we got a 3 over here is the base, 3 over here is the base. So we can go ahead and just set those exponents equal to each other. Let's see, that highlighter might pop up in a minute. Up, there we go. Perfect. All right, so go ahead and set those exponents equal to each other. Looks like I need a little bit more space here. My computer is frozen. Oh, there we go. That's okay. All right, so we're just going to set the exponents equal. Let's get back to my pen. So we have 1. Nope, that's not right. I'll use a different color since I'm switching to the exponent now. 1 equals t over 2. Now we need to solve for t, so go ahead and just multiply both sides by 2. It's going to cancel out on the right-hand side. You're left with t equals 2. Because 2 times 1 is 2. And that tells us, since t is the number of years from the time of introduction, that tells us it's going to take 2 years for the population to triple. So let's write that in. That's our answer. It's a different color. It will take 2 years for the population to triple. Now again, I knew that it was years because it says t represents the number of years from the time of introduction. So that means in order for it to reach the population to reach 897, which would be triple of the original amount of deer, that it would take 2 whole years for that population to reach that amount. All right, now we have a part B. It says, how long will it take for the population to reach 8,073 deer according to this model? So that's a lot more than our original value. Our original value of deer was just 299. But we're going to use this same idea. We're just replacing P of T, which is the current population, with 8,073. So go ahead, replace P of T with 8,073. Right-hand side's going to stay the same. Okay. Now we're going to solve for t. So approach this the same way. Divide both sides by that coefficient, 299. That was the initial value. All right, so that cancels out on the right-hand side. Looked like I just crossed off the 2, so I want to make it clear that it was the whole thing. All right, so let's see, what is 8,073 divided by 299? 8,073 divided by 299 is 27. So that's 27 equals 3 to the t over 2. Now again, we're trying to solve for d. We're trying to figure out how many years does it take to reach 8,073 deer. So we're trying to solve for this t right here. So we need to figure out, how can we make both sides have the same base? So how can we rewrite 27 as 3 to some power? All right, so let's go to our calculator. Let's try out some different exponents. 3 squared, of course, is 9. We're looking for 27. And there we go. 3 raised to the third power is 27. So 3 raised to the third power is 27. All right, so now they have the same base, so you can just go ahead and set the exponents equal to each other. So there's my exponents. I'm going to set those equal. So we have 3 equals t over 2. Again, multiply both sides by 2 to get t by itself. All right, so that tells us that t is equal to 6. So it's going to take 6 years for the population to reach 8,073. Okay. All right, so we've looked at a couple of examples of population growth or population decay. Let's look at a different application of exponential models. The next application of exponential models is called radioactive decay. Let me actually just add in a little extra page here so I can tell you a little bit about radioactive decay. All right, so radioactive decay is another application of exponential models. Radioactive substances diminish over time. So the model for radioactive decay looks just like the model for exponential, or excuse me, for population growth, except this time they use A instead of P. So they say A of T equals A sub 0, some initial amount, times little a to the t. All right, so that A0, A sub 0 is the initial value of your radioactive substance. And then A is going to be your decay rate. So A is called your decay rate. A will always be a number between 0 and 1. So we learned a little bit. We mentioned that in section 6.1 that when your base is between 0 and 1, that means that your exponential function is decreasing. So that makes sense here because we're talking about decay. So you've probably heard of this. You may have seen this in like a chemistry class with like carbon dating. We're going to look at some examples that involve other radioactive substances. So let's look at our first example. It says, the half-life of phosphorus-32 is approximately 24.3 days. So what that means is that that's how long it's going to take for some amount of phosphorus-32 to decay to half of what it initially was. So let's look at our example. It says, determine the value of little a so that A of t equals A sub 0 times A to the t, describes the amount of phosphorus-32 left after t days, where A sub 0 is the amount at time t equals 0. Round to 6 decimal places. All right, so what we're trying to figure out here is little a. Now, we don't know anything right now. We don't know what A sub 0 is. We don't know the initial value of phosphorus-32. We don't know the decay rate. We don't know the amount that we currently have, but what we do know is that the amount that we currently have is half of what we started with. All right, so we're going to say, okay, well, A of t, that's the amount of phosphorus-32 that we currently have. We know that it's half of what we started with. All right, so we know that the half-life is 24.3 days. All right, so we can go ahead and plug in 24.3 for t. And we know that after that many days, there's going to be half of our initial amount left. So you take and replace A of t with A sub 0 over 2. So that's the initial amount divided by 2, or half of the initial amount, equals A sub 0 times A raised to the 24.3, because that's how many days it takes for phosphorus-32 to decay to half of what it initially was. All right, so now we can work on solving for A. All right, so the first thing we need to get rid of is this A sub 0 over here. So go ahead and divide by A sub 0 on both sides. Okay, that's going to give us, move this down a little bit. Here we have A sub 0 over 2 divided by A sub 0. We can keep, change, flip. So that's going to be A sub 0 over 2. Change that to multiplication. Flip this bottom fraction. Right now it's over 1. So flip it so that it's 1 over A sub 0 equals A to the 24.3. Now we're just going to multiply this out. A sub 0 times 1 is just A sub 0. 2 times A sub 0 is 2 over A sub 0. Excuse me, 2 times A sub 0 equals A to the 24.3. Now you can see that these A's are going to cancel out. We're left with a 1 up here. We might have to end up moving this to the next page. All right, so we have 1/2 equals a to the 24.3. Now we're almost done. All we need to do here is get rid of this exponent, and we'll have solved for a. Now there's one way that there's really only one way that you can get a by itself here, but there's 2 ways you can write it. You can think of this as taking like the root of both sides. So you can say I'm going to take the 24.3 root of both sides. And a more simple way to think about it is to think, okay, well, if I was to get rid of this exponent, I could raise it to 1 over 24.3. So I could raise both sides to the 1 over 24.3 power. And that would cancel out on the right-hand side because 24.3 times 1 over 24.3 would just be 1. Power to a power, you multiply them. And now for the left-hand side, we can just plug that in our calculator. All right, so we have parentheses 1/2 raised to the 1 over 24.3 power. Now, if you have a TI-83, you want to make sure and put parentheses around your little exponent. So again, if you have a TI-83, make sure you put parentheses around that exponent. Let's see what that is. So here's our value for A. It said to round to 6 decimal places. So 1, 2, 3, 4, 5, 6. All right, so we're going all the way to the 8. We don't need to round up. So we have A equals 0.971878. Yeah, that's 6 decimal places. All right, so that's our value for A. That's our decay rate. Let's move this to the next page. Let's give it its own page so that we don't run out of or make it too small. Okay. All right, so let me just remind you really quick. Let's read our question first, sorry. It says, how much of an 11-gram sample of phosphorus 32 would remain after 5 days? All right, so let me remind you of our model. It was A of T equals A sub 0 times little a to the T. All right, so right now we know that our initial value of phosphorus 32 was 11 grams, so it's right there. All right, so A sub 0 is 11. We know that little a, we just found it on the last page, is 0.971878. All right, and we know that T, the amount of time that we're waiting, is 5 days, so T is 5. So let's just plug in our numbers, and we will plug this in our calculator. All right, so A of 5, equals A sub 0 is 11 grams. Little a here was 0.971878 raised to the 5th power because T was 5. All right, so let's just plug this in our calculator. Use all of those decimal points. Okay, so we have 11 times 0.971878 raised to the 5th power. All right, so there you go. After 5 days, there's going to be, let's see, it says round to 3 decimal places. So that's going to be 9.538 grams. Equals 9.538 grams left after 5 days. Okay. So that's an example with of an application of exponential functions with radioactive dating, or yeah, radioactive decay. Another example of an application of exponential models deals with financial applications. So we have what's called the compound interest formula. This is one of the most commonly encountered applications of exponential functions. You would use this formula, or this formula applies to your life if you have anything financed. So like if you have a car payment, or if you have a mortgage or a credit card, then your interest is compounded using this formula. All right, so here is the formula for compound interest. It is A of t. I'm going to tell you what all these letters mean. Equals P times 1 plus R over N, that's an R, raised to the N times T. All right, so write that down. I'm going to tell you what all those letters mean. All right, so A of T would be the current value. Let's say, we're going to call this actually the future value, I think is what your book calls it. This is the future value. P is what's called the principal. That's going to be either the amount that you originally invest or the amount that you originally finance if you bought a car or a house. R is your interest rate in decimal form. N is your number of compounding periods per year. We'll talk more about that in a minute. And then lastly, T is the time, or the number of years. We'll call it the number of years. Number of years. So this might be like, how many years did you finance the car for? How many years did you finance the house for? Notice that the capital letters in the formula, like A of T and P, represent amounts of money. All the lowercase letters represent something other than money. So let's talk about number of compounding periods in a year. Depending on what you have financed or what you have invested, the type of account that you're using, you would have different compounding periods per year. Now, the most common compounding period is monthly. So that would be like for your car loan or for your mortgage, interest is compounded monthly. So again, let me add in a little page here. And I'm going to move this little guy over just so we have plenty of room. So let me tell you the common compounding periods. Right, so these are the most common compounding periods. And then their corresponding N values. All right, so you could have annually, where interest is compounded annually. That means 1 time per year. So N would be equal to 1. You could see semi-annually. That means twice per year. So N would be equal to 2. Those are little arrows. Quarterly means 4 times a year, so N is equal to 4. And then the last one would be monthly, which would mean 12 times a year. There's other types of compounding periods like a weekly or daily, but these are the most common: annually, semi-annually, quarterly, and monthly. All right, so this might be something that you want to add to your index card for the next test. Let's look at an example. We're going to do a couple of examples that involve this compound interest formula. All All right, so this says Chester hopes to earn $1,100 in interest in 3.9 years from $11,000 that he has available to invest. All right, so he wants to earn $1,100 in 3.9 years time, starting with $11,000 that he has available to invest. To decide if it's feasible to do this by investing in an account that compounds quarterly, he needs to determine the annual interest rate such an account would have to offer to help him meet his goal. What would the annual rate of interest have to be? All right, so let's write down our formula and figure out what do we know. All right, so we have A of t equals P times 1 plus R over N raised to the NT. Now, we definitely know how much money he wants to earn. He wants to earn $1,100 in interest. So that's going to be his principal, which was $11,000. His future value of his account, he wants it to be $11,000 plus the $1,100 he's going to earn in interest. So that's going to be $12,100. All right, we know that his number of compounding periods, they said it's compounded quarterly, so that means 4 times a year. And we know that he's going to leave this money in the account for 3.9 years. So 3 years and 3.9 years, excuse me. All right, so let's plug in what we know and then see if we can solve for our remaining variable. All right, so A of t we decided was 12,100 because that's the amount that he wanted to have in the account after 3.9 years. Principal was 11,000. 1 plus, we do not know R. We know that N is 4. And we know that our exponent here is N times T, so that's 4 times 3.9. So let's go ahead and simplify that exponent. 4 times 3.9 is 15.6. So 12,100 equals 11,000 times 1 plus R over 4. That's an R. Again, it kind of looks like a V. Let me just rewrite that so that it looks. Raise the 15.6. Okay. We need to figure out how to get R by itself. The first thing standing in our way is this coefficient out front. So let's divide both sides by that coefficient because right now we're multiplying by 11,000. Oh, it's not straight at all. So 11,000. Divide both sides by 11,000. All right, on the right-hand side, excuse me, on the left-hand side, we're going to have 12,100 divided by 11,000, which is 1.1. Okay, so left-hand side is 1.1. The right-hand side, that cancels. So we're left with 1 plus R over 4 raised to the 15.6. Now remember what we did earlier to get rid of this exponent. We said we could raise both sides to the 1 over 15.6, and that would get rid of that exponent. Okay, so on the right-hand side, 1, if we're doing a power to a power, we multiply them. So 15.6 times 1 over 15.6 would just be 1, so that cancels. Let's see what we have over here. If it's a really long decimal, we'll just leave it. So 1.1 raised to the 1 over 15.6. Yeah, let's just leave it written as 1.1 raised to 15.6 right now. I may have said that wrong, but let's just leave it unsimplified for now so that we don't make any rounding mistakes. Okay, so on the right-hand side, we're left with just 1 over R plus 4. I said that wrong, sorry, 1 plus r over 4. We're going to subtract 1 from both sides. Leave it unsimplified, just write it out. 1.1 raised to 1 over 15.6 minus 1 equals r over 4. All right, then multiply both sides by 4. Okay. So we're left with 4 times 1.1 raised to the 1 over 15.6 minus 1 close parentheses equals r. All right, so let's plug this in. All right, so 4 parentheses, then a parentheses again, 1.1 raised to the 1 over 15.6. Get out of the exponent. So use the little arrow to get out of the exponent. Minus 1, close parentheses. Just typed it in exactly as I had it written there. Right, so we have 0.0245. Right, we need to convert this to a percentage because right now it's in decimal form. Okay, so if you are converting to a percentage, you just multiply it by 100. So that would be, it says round to 2 decimal places, so that's 2.45. So R equals 2.45%. So that's what he needs his interest rate to be to earn $1,100 in 3.9 years. Whoops. I don't know why it won't let me change the color all of a sudden. Here we go. All right, so that's our interest rate. This is probably the hardest one on the homework, I would say. Don't expect to see one like this on the test. Maybe one like the next example we're going to do. Let's look at it. This one says, Blanche has recently inherited $8,800, which she wants to deposit into an IRA account. IRA stands for Individual Retirement Account. And this is for, really anyone can open an IRA, but they're probably targeted towards people that work at jobs where they don't have retirement accounts. So if you get a job and your workplace does not offer a retirement package, then you can open up your own retirement account. It's called an IRA. The most popular one is called a Roth IRA. And this is the most popular because whenever you cash out your retirement after, say, like 40 years, 20 years, whatever, however long you invest your money for, you don't have to pay taxes on it. All right, so let's look at Blanche's situation. She's got $8,800 to invest. She wants to put it into an IRA. She has determined that her 2 best offers are, this first option is an account that compounds quarterly at an annual interest rate of 4.5%. So that's account 1. Account 1 compounds quarterly. And the interest rate we have to convert this to a decimal, so move the decimal place 2 places to the left. So start here, 1, 2. Fill in that blank space with a 0. That's 0.054. That's our interest rate. And her second option, account 2, is an account that compounds semi-annually. So that means twice per year at a rate of 4.9%. So move it 2 places to the left, 1, 2, fill in that with a 0. So that's 0.049%. Excuse me, that's the interest rate for that account, not percent. It's 4.9%, but as a decimal, it's 0.049. All right, so it says, which account would pay Blanche more interest? All right, so what we're going to do is just set up our equation. We know that our compound interest formula looks like this. All right, and we're just going to pick a random number of years. The easiest one to plug in would be t equals 1. So let's see which account is going to pay Blanche more money after a year. All right, so plugging in 1, so that's A of 1 equals, let's draw a little line here, let's keep them separate. She's investing $8,800 as her principal times 1 plus, interest rate is 0.054 for this one, over N, so it's compounded quarterly, so that means N is 4, raised to the N times T, so that's 4 times 1. Again, we're just randomly picking a number for T. You could use 2 years, 5 years, it doesn't matter. We're just trying to see which account is earning Blanche more money. All right, so let's plug that one in. Clear that out. All right, so 8,800 times 1 plus 0.054 divided by 4, close parentheses, raised to the 4 times 1. All right, so there's Blanche's future value after a year in this account. It's now $9,284.91. Oops, sorry. So that would be $92.84.91. All right, let's see if this second account is going to earn her any more money. Again, we're just plugging in 1. All right, so using our formula up here, make this big again. All right, principal is the same. She's depositing or investing $8,800 times 1 plus. Interest rate here is 0.049, so a little bit lower interest rate, but it's going to compound it twice a year. Semi-annually means 2 times per year. Raised to the N times T. So here we have 2 times 1. All right, so we got a lower interest rate and we got a lower number of compounding periods. So I'm suspecting that this will be her less. This one's going to give her less money. All right, so 0.049 divided by 2, close parentheses, raised to 2 times 1, which is just 2. And yep, there it is. So 92.36 and 48 cents. 92.36 and 48 cents. Which account would pay Blanche more interest? Account 1. All right, so account 1, she ends up with more money. So account number 1 is going to pay her more interest. All right. And then part B says, how much would Blanche's balance be from account 1 over 2.4 years? Round your answer to 2 decimal places. All right, so we're going to use our formula up here. We have A of T. I'm just going to rewrite the formula. Equals principal times 1 plus R over N raised to the N times T. This time, our principal is the same, $8,800. Our interest rate is 0.054. Number of compounding periods for account 1, it's quarterly, so N is 4. And T says she's leaving it in there for 2.4 years. All right, so let's plug all those numbers in and see how much, what her future value of her account is going to be after 2.4 years. A of 2.4 equals principal times 1 plus interest rate in decimal form over number of compounding periods raised to N times T, so that's 4 times 2.4. All right, let's plug that in the calculator. All right, 8,800 parentheses 1 plus 0.054 over 4, close parentheses, raised to 4 times 2.4. All right, so that's how much money Blanche has after 2.4 years, $10,009.00. That's a little money sign out there. Trying to make it look a little bit more legible. Yeah, it just made it worse. Let me see if I can try again. Not really. Not really any better. All right, so there we go. I like this one for the test, especially part B. So this is a good one for the test. Maybe that'll highlight that in just a second. I don't know why my highlighter takes so long to pop up. Yep, there we went. So part B is a good one for the test. All right, we have a couple more applications. And the last two are just sort of random applications. We're going to do one more compound interest, and then these last two are just sort of random applications. All right, so number 6 says, Quan hopes to earn $1,000 in interest over 4.5 years' time from $10,000 that he has available to invest. All right, so this is similar to the one that we did number 4. It says, to decide if it's feasible to do this by investing in an account that compounds annually, he needs to determine the annual interest rate such an account would have to offer for him to meet his goal. What would the annual rate of interest have to be? All right, so let's practice this again. Again, this is not something I would put on the test. I didn't mean to put this on here twice, but it doesn't hurt to practice this one again since it is kind of difficult. All right, let's write down what we know. We know that the principal that he's investing is $10,000. We know that he wants to earn $1,000 in interest. So that means he wants his future value to be the principal, which is $10,000, plus $1,000 in interest. So that's $11,000. We do not know his interest rate R. We know that it compounds annually, which means one time per year. And we know that he wants to leave the money in the account for 4.5 years. So 4.5 is T. All right, so let's plug in what we know. So we have A of T is 11,000 equals principal was 10,000. That's how much he originally invested. Times 1 plus, we do not know R. We know N is 1. And we know that N times T, that's going to be 1 times 4.5. Which is just 4.5. We know that R over 1 is just R. We'll go ahead and simplify that as well. All right, so we're trying to solve for R here. So let's divide both sides by 10,000. All right, it's going to cancel out over here. Now let's see, what is 11,000? Just doing this on my calculator really quick. 11,000 divided by 10,000 is 1.1. Same number as last time. Equals 1 plus R to the 4.5 power. All right, and y'all remember what we did here to get rid of that exponent? Remember we raised both sides to the 1 over 4.5 because this is a power to a power, so you'd have to multiply them. And 4.5 times 1 over 4.5 is just 1. Okay, so that's why that little property helps us, because that's going to cancel it out over there. And we're raising this side to 1 over the 4.5 power. All right, so on the right-hand side, that cancels. Remember what I said last time? Just leave it as 1.1 to the 1 over 4.5 so you don't have any rounding mistakes. I'm just left with 1 plus r. Go ahead and subtract 1 from both sides. All right, so on the right-hand side, that's going to cancel. Then on the left-hand side, you have 1.1 raised to the 1 over 4.5 minus 1 equals the interest rate. All right, so let's get our calculator. All right, parentheses, 1.1, close parentheses, raised to 1 over 4.5. Get out of the exponent, use the arrow button, minus 1 is 0.0214. Now this is in decimal form, so to convert it to percentage form, we can multiply by 100. This is the same thing as moving the decimal 2 times to the right. So that's it says round to 2 decimal places, so that's 2.14%. R is 2.14%. So that is what Juan needs his interest rate to, or excuse me, Quan needs his interest rate to be to earn $1,000 in 4.5 years. Okay. We have 2 more. Like I said, these are just sort of random applications. The first one we have here says the revenue function is given by R of X equals X times P of X dollars, where X is the number of units sold and P of X is the unit price. If P of X, the unit price, is equal to 27 times 4 raised to the negative X over 5, find the revenue if 15 units are sold. Round your answer to 2 decimal places. All right, so you may see this revenue function come up if you take an economics class. So we're going to take our little formula, R of X equals X times P of X. We know that X, the number of units being sold, X is the number of units sold, is 15. So we're just going to plug in X equals 15. All right, so we have R of X, or excuse me, R of 15 equals 15 times P of 15. All right, so here's P of X. So we're just going to plug in X there. So it's 15 times 27 times 4 raised to the negative 15 over 5, excuse me. I was about to write 4. Try that again. Negative 15 over 5. Okay. Now you can plug this straight in. Don't need to simplify anything first. Go ahead and go straight into your calculator. I like to start off with a blank screen. All right, so let's see. 15 times 27, parentheses, 4, close parentheses, raised to negative 15 over 5. You can simplify that if you want to. Negative 15 over 5 is just 3. All right, there you go. So it says the revenue, says to round to 2 decimal places. So the revenue is going to be $6.33. Because it said that the revenue is R of X equals X times P of X dollars. So this is money, 6.33. So not too bad. Probably the most common mistake is just to plug 15 in here and forget to use the revenue formula. All right, so don't forget to use the revenue formula like we did here. All right, last one says the concentration C of T of a certain drug in the bloodstream after T minutes is given by the formula C of T equals 0.07 times 1 minus e to the negative 0.2 T. What is the concentration after T minutes? Excuse me, after 10 minutes. Round your answer to 3 decimal places. All right, so super simple here. Just plug in T equals 3. All right, so we have C of 3 equals 0.07 times 1 minus e to the negative 0.2 times, and why am I plugging in 3? I meant to plug in 10. I'm sorry. I don't know where I got 3 from. Let's plug in 10. Because we're waiting 10 minutes. So 0.2 times 10. Close one. All right, so let's get our calculator. We don't have to simplify anything here. We can plug it straight in. All right, so 0.07 parentheses 1 minus, use that E button at second ln, negative 0.2 times 10. All right, so if you have a TI-83, you'll need to close the parentheses at that point and get out here, out of the exponent, close that parentheses. I'm just closing that parentheses right there. So there it opens, here it closes. There you go. That's the concentration of the drug after 10 minutes. So they said 3 decimal places, so that would be 0.061. They didn't tell us the units or anything. So we can leave it just like that. We're done. All right, so please let me know if you have any questions about section 6.2. Otherwise, I will see you guys soon. Have a good day.